Good morning. Let us come to the next series of lectures. These are the lectures will be focused on how to develop a mathematical models for the river. So, considering the basic concepts that the hydrodynamic principles of the basic modeling framework what you do it, and the same concept we also can use for analytical solutions of any river flow. So, considering that importance, I will go through some examples as well as the mathematical derivations. At the end, I will solve some numerical example. Let us look at again to talk about this. Mostly I have been following this book, Fluvial Hydrodynamics books, which talks about this hydrodynamics and the sediment transports phenomena very more detailed and very illustrative way to represent the hydrodynamic and sediment transport phenomena in the river systems. Also, I will talk about having a reference with river mechanics of P.Y. Julien's book, and also the stream hydrology, which is for introductions to ecologist. Not only that, we will have some of the reference from the standard journals like Journal of Hydrology, American Society of Journal of Hydraulic Engineering's Journal of Sediment Research. I do encourage all of you visit these journal sites and look at advanced level of research with what is going on in river engineering. Now let us come back to the today contents. So, let us start with the Brahmaputra river concepts, where I will talk about the scale problems, I will talk about the turbulent structures and energy dissipations, which are very complex process, and that what I will give at introductions levels. Before deriving the basic equations, let us learn it how complex the river flow in terms of hydrodynamic, in terms of sediment transport, in terms of nutrient transport mechanism in a natural environments like river. That is what we will discuss more details, how we can solve these river engineering problems. Then there will be a derivations for the continuity equations in 3 dimensions, the continuity equations for open channel flow, and then will be a series of the problems what will be solved to give you a confidence that understanding of a velocity field, water depth variations, those things you can get the idea while solving some of the example problems for basic mass conservation equations. That is what we will talk more details. Let us come back to the scale problems. So, we may have awareness about the Brahmaputra rivers. This is very the rivers which we call the braided river systems because of multiple unstable channels. Okay. And in between there are series of the bar or the islands are there, and that is what is intense sediment transport and active channel process what it happens it. And this river, if you look at this satellite data set, its length is about, the length of the river is close to 1000 kilometers, okay, and the width of the river, which is varies in a range of 1.2 kilometers to 16 kilometers, and the depth varies it on average of 12 meters. So, if you look at these values, one is 1000 kilometer scale, the length, the width is few kilometer scale, and the depth is in a meter scale. So, this is what we call the scale problems. That is what the scale problems with the river systems, because the dimensions of the rivers are not same dimensions, okay, in length, width and the depth, which is a considerably order of difference it is there. So, that is the reasons we need to have a lot of approximations to solve these river problems. It is not that simple way to solve a computational fluid dynamics problems, but the major issues come is the scale problems because of length, width and the depth. That's the regions. If we have classical examples of large sandbed rivers, as I said it, if you look at these figures, there are multiple channels are there, and these channels are quite dynamics, and there are very high flow and sediment variability. That's what I discussed earlier, and that's the reasons we should know it, how the flows are happening it, and which are very complex process what is happening it. And mostly again I need to emphasize about the scale problems in river flow systems, because this length, width, depth, the dimensions itself is a scale order difference. That's the biggest issue. Now if you look at another bigger issue, if you take a photographs of Brahmaputra rivers during the flood periods, you can see the turbulent structures, like for example this type of vortex formations. You can see from the taking the photographs, you can see that large vortex formations are happening it. There are the boil formations, which is that the vortex is formed from the ground and it's grow it and then it dissipates. So these type of process also happens in Brahmaputra rivers. And not only that, if you look at a bigger snap of photos, you can see the similar type of series of the vortex and boil formations happens it. And these are the macro turbulence structures. So these structures are also responsible for the flow behavior change, the velocity, depth, and also the change in the sediment transport process. The sediment transport process, because of this presence of the boils and vortexes is at the different or macro turbulence presence, make the sediment transport process in terms of source, in terms of deposition, in terms of transport process. That's what it changes it because of the presence of the macro turbulence. Now if you look at this, what could be the dimensions? Okay, the dimension as high as it can go to the 75 meters and or 240 meters above the sand waves. Okay, it works like a sand waves and stay up to the 30 seconds. If you look at this, these turbulent structures are visible in Brahmaputra river during the floods. No doubt they are also responsible for the energy dissipations in the flow systems. So if you look at these macro turbulent structures, which is visible, it's quite visible in Brahmaputra rivers, but in other rivers also you can have a smaller magnitudes of the turbulent structures. Okay, and that's the turbulent structures. Try to understand it. The structures changes the flow characteristics, sediment transport mechanisms, as well as the energy dissipations. So that's what is contribute the energy losses in the river. So that's the new concept what we are introducing to you. Now if you look at very interesting figures showing to us that how many type of energy dissipations happen in the Brahmaputra river. Like for example, if you take a Brahmaputra river is about 100 to 20 kilometer length from Tezpur locations to the Guwahati locations, and if you can look at river expand and contract it. Okay, it's not a uniform width rivers. Okay, it expands and also the contracts it. This expansion and contractions also varies from seasons to seasons. Like for example, for the low flow, you can see channels which are activated. But in case of the monsoon, the high flow, you can see that what are the channels are activities there. The width is also expand and contracts seasons to season, month to month. That's what the expansion and contractions are there, which generally accepted is major energy losses as its river expands it or contracts it, as you know it from basic hydraulics properties. Not only that, the because of the presence of the turbulent structures, the macro turbulent structures, thus the turbulent structures what will be there, that is a major emphasis here, that also generate the energy dissipations things. Energy dissipations also happen because of macro turbulent structures. The expansion contractions losses, like as there is a expansion and contractions are happening as equivalent river width. That's what is also we have these ones. Not only that, if you look at these rivers, when you have the river belt is so large, you can have a presence of the vegetations, certain type of grasses, certain type of scrublands or the forest. So those vegetations also interacts with the hydrodynamics. So you can have a energy losses due to the flow vegetations interactions. There are the multiple channels over the sandbars. Okay, that's also is there, and there is a thalag line. The thalag line says that the deepest the channel, the deepest point where the channel point, that thalag line also have the variabilities during the monsoon flow and the low flow. So if you look at that, when you talk about the energy dissipations in Brahmaputra rivers, it's not only this frictional losses, okay, frictional energy losses, which is well debated in many of river engineering books, but what we are talking about beyond that, there are the possibility for energy losses because of expansion contractions, because of the bank erosion process, because of macro turbulent structures, as well as the shifting of the thalag lines in the low and medium seasons. So that way we try to understand the river in different perspective, like how the energy dissipations are happening it, because that what it controls it, how the sediment transport happens, how the flow variability changes, how it's make a more vulnerable for the bank erosions, how these bed forms of river changes are middle bed mega bed forms like sandbars, how these formations are happening. All this the knowledge we should have it, try to understand it, how a river does energy dissipations, river does sediment transport mechanisms, and also rivers how its flow as water flow as a velocity and turbulent structures, the depth and the width. Let me go to the next slides, which want to say that when you have a complex river like Brahmaputra rivers or any rivers is a natural systems, we should try to understand this river or try to find out the solutions for that rivers. One approach is that we can follow mathematically a set of equations we can have, and we can solve these equations to find out the basic characteristics of the rivers like the velocity, sediment concentrations, nutrient concentrations, the depth and the pressure field. What we do it, which nowadays we have a more emphasis, but I can say that each methodology having the complementary to each others, is not having any superiority that mathematical model does good work or physical model doesn't work it, or all are having the advantage and disadvantage. But as a river specialist, what do I look at, that all these options should be looked at, and all these three options like mathematical modeling, physical hydraulic modeling and the field observations, all the things we should conduct it to understand the rivers in terms of sediment transport, in terms of the flow transport, in terms of nutrient transport, in terms of energy dissipation. What we do in mathematical modeling? First, we find out appropriate control volume. That's what is, you know it from the fluid mechanics. You can follow some of the fluid mechanics U-tips what is developed by me. We talk about more details about the control volumes, Reynolds transport theorems, how to use the control volume concept for deriving mass conservation equations, momentum equations, energy equations. These are there in any fluid mechanics book, as well as you can follow the YouTube materials what is there on fluid mechanics by me, talking about emphasize that how to choose the control volume, how to choose a appropriate control volume so that you can solve the fluid mechanics problems. The control volume can be infinitely small or it can be as large as a Brahmaputra rivers. So you can decide what type of control volume you have to consider to solve your problems. Control volume can have a at the rest or it in a motions, or you can choose it what type of control volume you have to consider it. After the considering the control volumes, you can find out the basic physical equations for the mass, momentum and energy conservation equation. So, you look at this mass conservations, momentums and energy conservations, that is what we get a set of partial differential equations as a governing equations for us, as you know in a fluid mechanics. Then you talk about, because this is an all linear equations, we always most of the times we start from a numerical solutions of these the governing equations, which is today's is a it's a possible to have this. There are a lot of numerical techniques are there. You can find out what will be the numerical solutions. What we are looking at as a numerical solutions, that for a control volume for a steady reach, we try to find out how does the velocity varies. That means we talk about the velocity field. We can find out the accelerations field, because if you know the velocity field. Similar way, I want to know it how the sediment concentrations variability there as a suspended load, as a bed load, as a wasp load, how the sediment concentrations variability is there. That is what if I try to get it as a solutions. Similar way, if I talking about nutrient flow depth and the pressure field, basically we try to get it these characteristics of the rivers in terms of hydrodynamics, in terms of the fluvial, means with a sediment, nutrient and energy dissipations. We try to look at all these components from the rivers after conducting a numerical solutions of these governing equations, which are in terms of mass, momentum and energy equations is most often we follow in the fluid mechanics problems. The same version of the fluid mechanics problems customized for the river flow systems. Many of the times also we go for a physical models, okay, and for water and sediment transport. I will show some of the photographs in the later on. So, we can have a scale models, that means you can make a 1:100 scale model, and we can solve these problems. So, the scale is 1:100, okay. The 100 unit of the prototypes represent 1 unit of the scale models. So, that is way you can use a scale model in the laboratory. You conduct the sediment transport flow, water flow, then you measure all these, the velocities, water depth, sediment transport part. Once you measure that, then you can upscale it as your scale models to do prototype scale at the river scale. You can have some similarity non-dimensional numbers to upscale this data. What you measure at these plumes or the small channels, that what you can upscale to the prototype scale. Then we get it the velocity field, the depth, other sediment concentrations, all you can do it. But here also we have the biggest problems with scale effect, because you scale down the models from 1:100. The major issue is here also the scale effect, as you all also you know it. It's have a advantage, however disadvantages. The advantages here is that anybody can, the field engineer can have a insightness what is the flow is happening it, and he can give a appropriate the suggestions to modify these physical models. So, still now there are many places we use the physical models as well as the mathematical models. They are complementing each others. But how accurate this physical model and mathematical model to real conditions, we have to have the field observations. This field observations is very critical nowadays. That is what is possible nowadays, that we can conduct the field observations with the advanced equipment like ADCP, acoustic Doppler current profiler to measure the velocity field and sediment concentrations, the water depth, all we can measure it, and those measurement of the data can be used for the mathematical model to validate or the physical model to validate that whatever the results we are getting from mathematical models or the physical model, are they accurate, are their performance are acceptable for river engineering practice. Those we get the confidence based on the comparisons with the field observed data with mathematical models, field observed data with the scale models. So, that is the reasons the field observations is always need to be do it before conducting any mathematical model or the physical models. No doubt nowadays we have another source is that satellite based, we can have the data, we can get the depth, width, the planform and sediment concentrations. Just time to highlight the things, we are not going detail anyway. In next classes we look at how to bring this advanced measurement of the river from the satellite platforms in terms of the depth, width, the planforms and the sediment concentrations. Some of the case studies I will show you in a later part of my lectures. Let us start to derive the continuity equation in 3 dimensions. Before that, let me talk about that you have to consider a control volume. And basically when you try to derive the continuity equation in 3 dimensions, our control volume is infinitely small, is very small control volume we consider it. And we also assume the velocity field, the depth variations, area variations. If you look at this case, as we know from basics definitions is that the mass flux, the mass per unit time, that is mass flux is equal to rho into q, the density into discharge. It gives us the mass flux or rho u a. So, here I am talking about u velocity component and the u. So, the discharge you have written that. So, the basic concept what we are using it, the mass flux is equal to rho into q, and if I write in terms of velocity, I have the rho u and a is the surface area. So, I can compute the mass flux passing through a control surface as a function of density, the velocity, scalar component and the area. That is very basic things that we can compute the mass flux. See, if this is the control volume which is having the dimension dx, dy and the gz. Okay, so smaller control volumes, and we are considering the u is a continuous functions and the velocity vectors which have the scalar component of small u, small v and w in a direction of I, j and k, that is x, y and z directions. If I have that as a velocity scalar component, and these scalar components are also the function of space and the time, and similar way the density is also functions of the space and the time, if you are considering that. So, basically what I am talking about, we go through any fluid mechanics basic things, that if I consider this, the density and the velocity are the continuous function in terms of the space and the time, and if I consider this is my control volumes, I just to find out how much of mass flux is coming into the systems and going out of the system. That is what will be indicating me that net change of the storage in the mass within the control volume, which is a basic concept, and if you can go through Reynolds transport theorems to consider that, but looking at in this case a small control volume here, I just try to know it, what is the net mass influx is going in x directions, net mass influx is going in y directions, the net mass influx is going in z directions. That summation should be equal to the mass change in the storage of this control volume. That is a very basic things, that influx and outflows, and you can find out the net influx passing through these control volumes, and in a x directions, y direction and z directions, just summing up, and also we know it what could be the net storage of the mass which is happening within this control volume. That is what you equate it as a mass conservation principle. That is what we will get the equations. So, let us just look at these derivations, that we are looking at a very small control volume with having a dimension dx, dy, dz, and it have a velocity component, scalar velocity component uv small w's, which is in x, y, z directions. If you can see this control volume, I am just computing the mass flux. Before computing the mass flux coming through this, these are going out from this, only I have to know it as the mass flux. What we can define it is a rho u, and dy by dz is a surface area perpendicular to the u directions. This mass flux, if you look at it varies along the x directions. If considering the first term of the Taylor series expansions, you can get it the rho u, the variations in the delta x directions will be rho by delta x rho u dx by d2, that is the distance from the centroid, by dy dz. So, this is the Taylor series expansions to estimate it if a functions varies at the dx by 2 distance, what could be the value. Same way mass influx, that is what we also compute it at this surface will be the rho u minus of this, because minus dx by d2 is just back of this centroid plane. So, minus dx by d2. So, you can get a mass flux that. So, this is simple Taylor series expressions, you can use it to compute it what is the mass flux is coming from this surface and going out from this surface. Then we can compute net mass flux, which is very simple. That is what is in net mass influx passing through this x directions. I explained it, and this is what we will have a the net influx of mass in the x directions. We will have a just subtracting of these two, we will get it this part. Okay, these two are cancelled out each other, and dx per dt will be combine it. You will get it a net mass flux out in the x direction through the two surface faces. It will be this part. Same way you can do for y directions, also we can do for z direction. If I combining that, so all the other two directions I can do it, and so net mass outflux will be this is the x direction mass, this is the y directions, and this is the z directions, multiplied with the dx dy dz is indicating for us the net mass influx in the x direction, y direction, and the z direction. So, you know from this control volume what is the net mass flux is going in the x direction, y direction, z direction in terms of a function of rho and u. Rho is a density, u is the velocity scalar components, okay, in the x direction. Similarly, rho into b is a scalar component in the y direction, and w is the z direction. So, we can get it the net mass flux out of the control volume is coming up to that. Based on the mass conservation equations, this net mass outflux from the control volume becomes will be 0. The net mass changing with the control volume will be rho into the volume. That is what is by rho t, it will give us the rate of change of mass with respect to time. That is what will give it a rho into p volume. That is what if you look it and change with respect to time, the rho because del rho by del t, that is what will be gives us the rate of change of the mass in the control volume. That is if you 2I equate it, I will get it these equations. Okay. If you look at this equations part, this is the net mass influx in the x direction, net mass flux in the y directions per unit volume, net mass influx in the z direction per unit volume. This is the net storage mass, rate of change of the mass storage within the control volume. That is what we represented like this. So, if you look at the next part, that many of the times we try to look at fluid is incompressible, okay. Density does not vary it, but that may not be conditions for river flow. So, that is what again I am to hypothesis that in fluid mechanics many of the time we simplified it, density does not vary it. But as we discussed earlier that we can find out the sediment water mixtures density which may vary it depending upon the concentrations. So, we cannot consider it as a constant parameters, but if you consider a constant parameters as water flow, as there is not significant sediment transport is happening, it we can simplify that equations which is there in any fluid mechanics books, okay. That is what will coming to be the steady flow, okay. It's also have assumption of steady flow, the flow does not change with the time. So, you can get it these components, okay. If you consider rho is a constant and rho does not vary with the time, and that is the steady flow and incompressible if you consider it, that is what is coming it. Again I want to highlight it, there are a lot of assumptions we have involved here, and when you solve the river engineering problems, please look at whether these assumptions is valid for us. If you have the two dimensional flow which is in x1 plane, you can drop these components and you can have the flow fields in only the x and z direction. So, your two dimensional flow and x z plane, the continuity equations becomes this which is in that fluid mechanics. In terms of shear strain rate, we can rate it this form, okay. Which is exactly this part, just to look at the some fluid mechanics books to try to understand that part. But some often we use a stream functions, okay, when you look at the river from the top, you can see the plan forms of the rivers, and if you can draw the streamlines, you can solve these problems. So, that is the reasons I am just introducing you the streamlines which are very basic in the fluid mechanics as the definition of the streamline, the relationship with stream functions and u and w is given like this. Then you can find out the change in the stream is a continuous to the second order derivative. The stream functions has this, if you put in all these values, you can find out the stream functions values, and you can find out the difference of the stream functions, like you have a streamlines and the difference of the stream functions, like you have a psi 1 and psi 2, difference of that will give a net flow what is going through these two streamlines. So, that very basic ways I am just revising you for the fluid mechanics things, stream functions also we can use for the river flow. Let us come for the continuity equation for open channel flow. So, we are coming from fluid mechanics to the open channel flow when you considering a river. So, in case of the rivers, what we will have, there will be lateral inflow to the river. If you look at this control volume, there will be lateral inflow to the river. That lateral inflow or the outflow, it depending upon from the surface as a rainfall or evaporation is going out, or there will be a exchange between surface and the groundwaters. Sometimes the river water goes to the groundwater or groundwater comes to the river waters. So, you will have a lateral inflow to this control volume which is quite different than other fluid mechanics problems. When you take a rivers, there is a exchange of the waters from river to the groundwater, groundwater to the river, and also the exchange of the waters from to the atmosphere, from the river to atmosphere or atmosphere to river as a raining to happen it. So that's the reasons we can say is a lateral flow happens to the control volume if I consider it. So there is a QL amount of the lateral flow happens, it fed laterally with a uniform rate. This is a quite simplified assumptions that QL doesn't vary with time, but we can do it. But let us consider within this control volume the Q is more or less uniform. If you are considering that, now if you see these figures, this is the control volume, this is the river, you have a river shape, and that is what is say that unsteady open channel flow. Solid line shows the initial condition, whatever the solid line it is indicating is initial level t equal to 0, that is the conditions. At the t equal to delta t, your surface becomes a dated part. Okay. There is change of flow depth, the change of the storage, there is a change of the velocity field with from the t equal to 0 initial time step to the delta t times. So, if is my control volume this, with this lateral flow I want to derive this mass conservation equations. That is the basic idea, to derive mass conservation equations. We will talk about how the storage is changes it, how this mass influxes are changes it. These terms we will discuss it more detail in the next slide. If you look at come back to the initial delta t time in mass flux, we will have the mass influx is coming is a rho u a dt, that is what is mass influx is coming it in time dt, plus you have the lateral flow which is coming into this control volume, which will be QL time of dx. So, lateral flow is per unit length into dt. So, this is for the lateral flow part, and this is the what mass flow. U here stands for area average flow velocities. Okay, it is area average flow velocity. A stands for the flow area in the left section. And if you look at the mass influx in time delta t, in this case you have a u and the a is a variable. So, after delta t times you can consider u vary to u plus delta u, a varies from a plus delta u. That is the reasons the mass efflux are going out from this control volumes will be the rho into a u, the change of the velocity and change of the area into the delta t. That is what is the mass efflux or the out from this control volume, and mathematically you can derive it as u and a is a function of in the x directions. That is what we can define it as a u and a this form. And if you look at that is what is there here, the area average flow velocity A stand is a flow area, and that what in a different time. Now, if you look at the net increasing of the fluid mass in the control volume, okay, within this control volumes, that is what will be net increasing, so will be rho into the volume, okay, by the delta t. Okay, that is what is rate of change of the mass, okay, with respect to time, rho into volume. In this case we have this the volume we write in some t is a top width, h and delta x. As we have included h is varying with respect to time, so delta is by delta t and delta t is component is there. That is what is the mass rate of the change of the fluid mass in delta t time comes out to be this. So, I know influx, I know the outflux, I know the change of the things, just I have to equate it to get it the basic equations. So, the influx part, the outflux part, that is what the net change of the mass within this control volume, which is the open channel control volume with lateral flow of QL per unit length. So that way you can look at these equations, which is just a mass conservation equation of influx, outflux and change in the mass within the control volume. That's what, if you simplified it, it comes like this. Okay. So if you these equations you can just simplify it, it will comes that, and if you write Q equal to UIA, area is a top width and the DH value, then this equation again simplified it as just a transport equations of the partial derivative of Q in x direction, area with a time derivation, that is what equal to QL. Be remember it is a mass in conservation equations, but when you write down in a partial differential equations form, that is what is come terms of Q variability x directions, that is the gradient of the Q in the x direction, and the A variable is equal to the QL. You can substitute the unit of the all these terms and verify are there accurate. Okay. The similar way, if I define the hydraulic depth is a area by the top width, you can get it expanding that not in terms of Q, in terms of capital U, which is the area average velocity, and the H I will get this equation form and without lateral flow. This is the equations is long back given by De Saint-Venant 1871. So if you look at these equations, if you can remember this, you can simplify this and this, only the things are there, certain assumptions we have. Like for example, this is no lateral flow, the equations becomes this is very simple things, okay, with discharge per unit width. If you have a, in terms of a hydraulic depth, in terms of velocity, if you try to equations, you are like this, and if you want to have a, in terms of Q and the area, your equations will be like this. But all these are derived equations from these basic mass conservation equations, which again I am to show you the basic control volume. To understand it always, you try to sketch the control volume. If you try to sketch the control volume and find out a mass influx and outflux rate, and just write a mass conservation equation to solve these problems, and just try to know it, what are the dependent variables you are making it, or what are the flow variability you are making it for these control volumes. Like for example, for this case we are considering as the river is open channel flow, there are lateral flow we have given emphasize, there will be lot of exchange of the flow of waters to the river or out of the rivers, that is what is we are defined is a lateral flow. And here the mass influx we define in terms of rho into U, U is the area average the velocity component, that is what we are looking in only this x directions. So we are not having a 3-dimensional, we are just looking it in the space only x directions and the time. So you have a rho into U, that influx and outflux you compute it, and you compute the change in the storage part, that is what you equate it to find out basic mass conservation equations. So basic things what I to tell you that first you choose the appropriate control volume, find out the influx and the outflux and the change in the storage of the mass within the control volume, equate it. The equation may be a partial differential equations, but the basic concept is the mass conservations applied to a control volumes. Like for a river, like a problems where we consider only longitudinal directions and dominated directions as well as the lateral flow part also we have considered here. Looking that back before concluding, I can have a few examples to just to give you a confidence that we try to find out the velocity fields, okay, when we solve these problems, okay. Like for examples, if you have this example 1 in the fluid flow, you have a velocity field and density fields, which is given is a velocity vectors and the density as a function of the space. does it satisfy this flow continuity equations at x equal to 1 and y equal to 1. So, this is simple. Since only x and y is there, time is not there. So, we can find out is only the two dimensional flow equations, mass conservation equations with a rho and u, and if you just substitute, this is the two dimensional steady flow equation, just substitute all these equations, finally you can find this equation and substitute x and y, this is not coming to 0. So, that means it does not satisfy. So, just to give you that, many of the times you can have analytical functions to find out do they satisfy the continuity equations or not. Same way, next examples, the solved example in open channel flow, the velocity field is defined it here, which is x, y, z component with a function of x 2s square, 3y square, 2z square. Density is given a function of 3s square t square. Does this satisfy the continuity equations x, y, z equal to 1 and t equal to 1. So, same we can use the continuity equations, substitute all these values, you can have a just partial differentiation of this equations part, then you substitute, finally you will see that, and when you substitute x, y, z, t on these equations, this is what we found out, it does not satisfy the basic equations for x equal to 1, y equal to z equal to 1. So, this does not satisfy it. So, this is what is very simple examples is given you to get the idea that we can look at whether you can have a solve this problem. These are very simple problems, again in a one dimensional open channel flow, that is when we are talking about only x directions. Discharge is defined as a 2s square by meter cube per second. So, area is given as a function of t and x, find out the lateral flow x equal to 0 and t equal to 0. So, they basically you want to find out del q by del x, del a by del t, and then you substitute to find out what will be the QL. So, you can partial derivative this part and then you put it this, and x equal to 30 meters, t equal to second, if you substitute it you will get this QL. So, in these are quite interesting problems where q is given a function of x, area is also function of x and t, and we want to find out what will be the lateral flow if x equal to 30 meters and t equal to 60 second if it follow this mass conservation principle. So, it is basic just applying this mass conservation equations. With this let us have a completing 2-day lectures. Again we will discuss a few example as well as the momentum equations in the next class.